Hi everyone, my name is Kiran. Today we are going to track the full arc of logical decoding and replication. We'll go from its earliest building blocks in PostgreSQL 9.4 all the way to the multi-master distributed future that's being actively built right now. Let's dive into past, present, future of logical decoding and Postgres logical replication. This is an important topic. Quick one. Who am I? 20 years with databases and the last 5 years building a Postgres startup. So, yeah, I have seen both worlds. I'm the founder of OpenSource DB and I love building communities. Hyderabad Pug, Vizag Pug, and Postgres Women India. I speak at Postgres conferences, teach as an adjunct professor, and I'm a strong open source evangelist. Before this, I had stints at General Electric, Optum, Oracle, Second Quadrant, and EDB. So, yeah, I have looked at different ecosystems. So, if I sum it up, Postgres, community, and startups, that's my zone. Now, let's look at what we will cover today. Right, here's our roadmap. We will start with the past, where logical decoding came from, how extensions like pglogical outlook shaped the ecosystem before native support in PG10 existed. Then we will move into the present, looking at native logical replication features from PG10 through PG18, including CDC pipelines, real world deployment patterns. After that, we will look at the future DDL replication, the multi-master architectures, and what the community is building for PG19 and beyond. And woven throughout, we will do an architecture deep dive into the internals wall, output plugins, and replication slots, so you don't just look at these features, but how they work under the hood. Let's get started. You would have seen, physical and logical replication. Before we dive into the history, let's make sure we are all on, the same page with respect to the replication topologies and the architecture. The logical replication actually is, and how it differs from physical replication. Everybody would have seen physical replication, right? It is shipping the raw wall bytes from primary to standby. It's an exact block level copy, which means standby runs the same major Postgres version. You replicate the entire cluster, and the standbys are read only. In contrary to the logical replication, right, it slightly works differently. Instead of copying raw bytes, it streams the row level changes based on the replication identity, typically the primary key. This gives you some really powerful properties. You can replicate across different Postgres major versions. You can selectively choose which tables and even which columns of rows, thanks to some of the row filtering features that were introduced in the latest releases. And critically, it opens the door to multi-master setups where multiple nodes can accept writes. The important thing to know is that both mechanisms can run concurrently in PostgreSQL. You can have a physical standby for HA, you can have a logical replication for CDC or cross version migration on the same cluster. They can coexist. And moving on, let's look at the logical decoding, how it actually works under the hood. This architecture is fundamental to everything else we discuss in this 20 odd minutes. It starts with the wall. When you set wall level is equal to logical, PostgreSQL starts writing additional information into the wall that allows it to reconstruct all the logical changes, not just the raw bytes, but the actual row level inserts updates and the CRUD operations that are happening on the primary server. That wall data that passes through the logical decoding layer, and this is the engine that reads the raw wall records and translates them into a stream of logical change events. It handles transaction boundaries, the snapshot management, and the ordering guarantees that make replication super reliable. Next comes the output plugging, right? This is the output plugging where the decoding changes get formatted for consumption. Postgres ships the output plugin called as PG output. And this is the default plugin used by the native logical replication. But there are alternatives like wall to JSON, which formats the changes as JSON, which is popular in the CDC pipelines. And test decoding is another popular plugin which is useful for debugging the changes that are happening on the primary systems. Finally, thanks to the 9.5 feature, we had something called as replication slots. This is the persistent mechanism. A slot tracks every wall file, right? Each consumer has read up to that wall stream or not. If a consumer disconnects and again reconnects after a planned or an unplanned outage, it picks up right where it left off, right? Slot persists across server restarts, right? Which is the powerful feature that some of the planned outages can have, right? But it's also something you need to monitor carefully, right? Because an active slot will prevent all of your walls to be not cleaned up, which will again bloat your storage. We'll come back to that slots aspect in our performance section. At the end of this pipeline sits the subscriber, right? The target logical subscriber. That could be another Postgres instance, or it could be an external CDC consumer like Debezium, feeding into Kafka, which has been a really important use case in the CDC pipeline ecosystem that we learned. Now let's look at the past, right? What was the foundation that was laid as part and parcel of Postgres 9.5? Now let's rewind it a decade or a decade and a half, right? Postgres 9.4 was the first release where there were the building blocks for logical replication, right? Now that introduced into the core of the Postgres. And Postgres 9.4 gave us three critical primitives. Right? First, replication slots that persist the tracking mechanism I just described about. Second is the replica identity for the table level parameter that controls what information gets written to the wall for updates, deletes, and the CRUD operations. By default, Postgres uses primary key, but you can also set it to a full by using the replica identity and write the entire old row or nothing. And then the third is the logical decoding API itself, right? The framework that plugs that can use the entire decoded changes and then push it across to the target instance. But here are the things 9.4 gave us, right? The API, but not the complete feature set. There was no built-in create publication. There was no create subscription, no publication on the source, and subscription on the target side, right? We always needed an extension, like I mentioned, PG logical and PG logical output. That's where the extension pglogical came up, right? And then it built the full publish and the subscribe model, and on top of the 9.4 logical decoding API. It supported row filtering, conflict detection, and was the technical foundation for the entire bidirectional replication, right? The BDR 1.0, which was a completely open source extension we had, right? In 2017, Postgres 10 brought native logical replication into the core with publication, subscription, syntaxes, right? That's where we say create publication, create subscription. We will see an example in one of our slides, right? This was powered by the PG output plugin. This feature to a first class Postgres capability. Now, let's move on and see the evolution from Postgres 10, where we introduced the first native logical replication till the current major version of PG18. One logical replication, indeed, landed in core of, PG10. The community just did not stop, right? Every subsequent major release has added meaningful improvements. And this slides gives us the entire timeline. What happened on PG10, what happened in 13, 14s, 15s, and so on and so forth, right? But let's just, double click on PG10. It gave us the basic publish and the subscribe model, right? And then PG11 added the truncate replication. Previously, truncate was not captured by some of the logical decode, right? Now, PG13 was important because it introduced the logical decoding in progress, right? Now, the in progress transactions. Before that, very large transactions. We are aware that some of the applications perform large transactions would only be decoded after the commit, which means there is a million records that are being processed on the source side. You could only look at decoding them and sending across to the logical replica after the commit, which could cause massive lag spikes, right? The real game changer came in PG 15 and 16, right? 15 gave us row and column filtering finally, right? Now you could just publish only a subset of the rows, right? Now with a where clause. And you would appreciate the fact that off of the entire 10 million table, you want to broadcast only a million or a few hundreds of case of records and choose exactly which columns to replicate. PG16 added parallel apply, right? Multiple workers processing changes. Currently, uh, and concurrently, binary node of the initial table copy, which is significantly faster. And then, another important feature was the failover of replication slots that came in 70, making logical replication viable for HA architectures. And in PG18, which shipped in last September 2025, brought us the detailed replication support, conflict detection and monitoring, and parallel streaming as the default. Each of these releases, when we look at some of these blocks, right, the foundational blocks from the 9.4 world to the 10 to the 18, right? So we've been building towards making native logical replication truly production ready, right? And I'd argue that as of PG18, we are now far more ahead of the curve when it comes to the replication. Now, let's look at some of the 15 and 16 production ready replication, right? Let me zoom in on two important features that I think were the biggest inflection points, right? Row and then the column filtering in PG15 and the parallel update, right? And then, most of you all have seen the new GUCs that were introduced, right? Max parallel apply workers per subscriptions. Row and column filtering, fundamentally changed what's practical with logical replication. Before PG15, a publication was all or nothing, right? You publish the entire table. Now you can write something like, I will create a publication for a specific table called orders, where region is equal to APAC, and only APAC region orders get replicated to the subscribers that are there in place, right? Lists, similarly, you can choose to publish only specific columns. This has huge implications, assuming you are looking at a multi-tenant architecture. Data sovereignty compliance is a very important feature, or the offering that some of the platforms do, and simply reducing the bandwidth and the storage costs of replication. If you are running a SaaS platform and you are in need to replicate customer data to regional clusters, this is the feature that makes it practical without having to reconstruct your entire schema. And then another feature, parallel apply in PG16, addressed the major bottleneck of the throughput, right? The throughput between the source and the target. Before 16, a single apply worker processed all the changes in a sequential manner, right? If your publisher had a high write rate, the subscriber would fall behind, naturally, because the velocity at which the changes are happening on source versus how they are applied. With parallel apply, now Postgres can use multiple workers per subscription, right? That's the GUC that I was referring to, applying non-conflicting transactions in a concurrent way, right? Combined with binary mode for the initial table synchronization, which skips the text conversions step. PG16 dramatically reduced both initial sync and the steady state of the replication lag. And moving on, right? What is the the latest advances that we have made in the PG17s and 18, right? Continuing the momentum. Failover replication slots in PG17 solved a real operational pain point. Before this, if your primary failed over to a standby, your logical replication slots were lost, right? Subscribers uh, wouldn't disconnect, potentially needed a full resync. PG17 allows slots to survive failover, and the new PG create subscriber utility, right, makes it pretty straightforward to convert a physical standby. Right? A physical standby, you don't need any downtime per se, right? That physical standby was transformed into a logical subscriber, which is incredibly useful for a zero downtime major version upgrade. Now we'll talk about that zero downtime upgrades in a moment. And then in PG18, the headline for logical replication is the conflict detection and monitoring, right? The new PG stat subscription stat views gives you a per subscription counters for different conflict types, the insert conflicts where a row already exists, update conflicts where the origin differs, missing row conflicts. This visibility is essential if you are running any kind of multi-node topology. In PG18, it also lets you replicate stored generated columns, so which was a pain point for most of the database models. When your subscribers are non-Postgres systems, they can't recompute those values, and create subscription now defaults to parallel streaming mode, right? So you get better throughput throughout the no, out of the box without any manual tuning. Now moving on, native versus extension based. This is the comparison that I wanted to look at, right? So given all the improvements in core, right, and I wanted to touch upon extensions like pglogical, Spark, and BDR. Where would they fit in, right? But look at some of the advanced features, right? DDL replication, just arrived in PG18, right? Extensions like, BDR, PG8, Spark extensions have had that auto DDL for a while, right? And conflict resolution in core is still, basic level of monitoring, gives you detection and monitoring, but not the sophisticated last writer wins, first writer wins, and some of the conflict handlers that the pglogical and Spark extensions provide, right? And then the big one in PG18 is the multi-master replication, right? Native Postgres still does not support it completely. pglogical has had a partial support. You can set up bidirectional replication with some conflict handling. BDR and Spark offer full multi-master mesh topology, right? Uh, Bottom line, if you look at the use cases, they are straightforward, right? If you have a pub sub replication, CDC, or a cross version migration, right? Native logical replication is now excellent, right? You need multi-master, advanced conflict resolution, or automatic DDL synchronization, in complex topologies. Extensions still lead you there. Now, let's look at the use cases, right? The change data capture. Right? Let's talk about this super important aspect, right? The CDC. This pipeline is probably the most common production pattern. I don't know. Your Postgres database publishes changes through a replication slot. Those changes are consumed by a CDC pipeline like Debezium, right? It's a popular option which feeds into a streaming platform like Kafka. From there, downstream consumers can, push it to a data warehouse, analytics engines, ClickHouse is a good example, which can consume those events, right? Why logical replication is the right foundation for CDC, right? It is fast, minimal performance impact, right? Before we were reading from the wall, there's no trigger overhead, right? Your OLTP performance isn't affected by the CDC, right? Secondly, right, transactional consistency. Changes are delivered in commit order. You never see a child record before its parent, right? So the asset compliance, you will never see a partial transaction. This is the guarantee that polling based or time based CDC approaches simply can't provide, or no, it cannot give you that compliance. Third is the flexible output formats, right? The PG output plugin gives you an efficient binary format. Vault JSON gives you JSON and, easy parsing. You can write even custom output plugins for specialized needs. Spark is a good example. And the last one, the zero downtime migration. Now, set up a logical replication to new Postgres version, let it catch up, the cutover lag is zero, combine it with the PG create subscriber. The workflow is now, remarkably streamlined. Now, let's look at the quick setup that we can do with a simple set of commands. On the publisher, you need three configuration parameters, right? Wall level, and then your max wall senders and the max replication slots, right? The default values are good enough for max replication slots and the wall senders. You got to change only the wall level from replica to logical. On the subscriber side, it's a single SQL statement, create subscription, pointing at the publisher's connection string and the publication name, right? Postgres handles initial table syncs and then, starts the entire, streaming changes from your source to the target. Now, look at the more advanced SQL example there, right? Which is 15, PG15. You can create a publication with row filter, like I said, right? You're saying, region is, specifically US. You want only those matching rows broadcasted. And then, you can specify exactly which operation to publish, whether you need an insert, whether you need a delete, or you need any combination of them. And with 18, you can now monitor replication health programmatically by querying pgstat subscription stats. right? These conflict counters are, I mentioned earlier, conflict insert exists, conflict update missing, they are all right there in the system view, right? Now, let's look at some of the real world patterns that are emerging, right? Let me quickly walk you through four production patterns that we have been seeing where logical replication is making a huge difference. Zero downtime migration upgrades. This is probably the most common use case you set up, and in a logical replication for your PG16 cluster to a PG18. Once the subscriber catch up, you are good. Right? You can do the upgrade. And the PG upgrade brings in that uncertainty, in a large database that could be avoided. Multi-region data distribution, right? It can replicate subsets of your data to regional clusters. And the real-time analytics pipeline, we talked about, the CDC ecosystem, right? From your OLTP systems through the Debezium Kafka of ClickHouse, right? Now, database consolidation is an inverse pattern. Multiple source databases, each published to a single subscriber for centralized reporting and analytics, right? So that's one of the important stuff, I would say. Now, moving on to the performance tuning and the gadgets that I wanted to double click on, right? On the best practices side, prefer logical identity using index over replica identity full, right, on the large tables, because you are going to be constructing a lot of full writes. Enable parallel apply if you are on PG16 and later, right? No, that the GUC that I referred to, right? And monitoring the replication lag continuously with pgstat replication. The max slot keep wall size to limit how much of wall an inactive slot can retain, and use binary mode for the initial table copy. It's significantly faster than text mode, right? And then missing primary keys will break the replication updates and delete. So any changes that are being happening for the schema needs to be applied onto your logical replicas. And then long running transactions on the publishers block slot advances. Now let's move to the future of it, right? The distributed databases, the multi-master system, right? The holy grail of many Postgres users is multi-master replication, right? What you see on is slide is three Postgres nodes geographically distributed, each accepting both reads and writes with changes flowing through bidirectionally between them. Like, this is active replication. The key capabilities needed for this are active writes every node handles, and the reads and writes simultaneously. Right? Automatic conflict resolution where two nodes update the same row concurrently. The system needs a policy. Last writer wins based on timestamps is the most common one we were looking at. Right? Who is building it today? Fiji Edge with their open source Spark extension provides multi-master replication for community Postgres. EDB is BDR, and the most once in 5 nines availability, and Postgres community itself is contributing foundational pieces, conflict detection in PG18, the sequence replication, failover slots that are building towards the future in core, right? And the horizon, I would say, right? What is there in in PG19 and beyond? Google has been contributing significant work on automatic conflict detection. Sequence replication is maturing. A structured conflict log, a dedicated table for conflict events. Parallel PG dump improvements combined with logical replications will make that initial data sync in large migrations really faster. And the big question, uh, will active replication land in core? The honest answer for me is the community is building towards it incrementally. Each release adds another foundational piece. PG18 added conflict monitoring. Future releases may add more and more conflict resolution policies. Now, looking at the key takeaways, the key takeaways that I would say are the five important ones. What I have here is uh, logical decoding laid the foundation, native replication in PG10, and extensions like pglogical, Spark, and BDR pushed the boundaries. And then the fourth and then the fine important pieces are the CDC pipelines and the future of distributed databases, the active PostgreSQL that is being built into the open releases, right? And that brings about the last of my slides. Now that's everything I have got for you. Thank you so much for spending this time with me at Posette 2026.